Okay, so we're going to take a look at electrons within the atom. So last chapter or last section, we were talking about the nucleus and protons and neutrons and mass and what's going on inside the nucleus. And now we're going to take a look at the outside of the nucleus and the electrons that are in this kind of cloud around the outside of our atoms. So these are responsible for the chemistry. So what we're going to notice is the electrons are going to be responsible for how atoms react. And with that information, we're going to be able to kind of predict what types of ions they form, whether they're going to have a positive or negative charge, and a bunch of other attributes based on the electron configurations or how many electrons are around an atom. So this, in order to discuss electrons, we don't really need to discuss this, but it gives you a better idea of kind of where all of this stuff comes from. So if we have some continuous source of light, and when I say continuous, it's going to be a white light, essentially all the colors of the spectrum. If we check out the spectrum that it produces, like if we were to put this through a prism, okay, so if this is a prism right here, it's going to divide light up and it's going to give us all of these colors from red all the way to blue or violet, but blue. Okay. So in a perfectly white light, we call this black body radiation as chemists and physicists. Black body radiation is essentially the idea that if you heat something up until it's white hot, it has like all of the spectrum, all of the colors in it because of the source of light that you get. So it's got all of the colors of a rainbow, and that's exactly what we see. It's got every single color. Interestingly enough, if this white light source is passed through a cloud of hydrogen, so it's just hydrogen in here, so there's just a bunch of hydrogen atoms and hydrogen molecules, we see something interesting happen. So chemists or physicists did this where we put a light through here and it again gave us this spectrum, but we noticed that something was missing when the light came out. What we noticed was missing is these little spectral lines right here. So we had the red all the way to blue, purple, but we are missing a bunch of lines and they actually look black. You can't see those colors. So these missing lines tell us something is going on. Something is going on. What ultimately is happening is a hydrogen is absorbing the light. But more importantly, the hydrogen is absorbing very specific wavelengths of light. So it's always absorbing, and hydrogen will always do this. Will it absorb these very specific wavelengths of light? And so as chemists, we're like, what is going on here? Why do we see these gaps missing? And how and what is hydrogen doing here? Well, it turns out that if we look off to the side, or rather, if we excite, so this is going to be a emission spectrum, or I'm sorry, this is going to be absorption spectrum. This is what you see when you actually excite hydrogen. And if you excite hydrogen, you actually see those same lines. You can't see all of them, but you should be able to see all of them. So what you end up seeing is those lines show up. So every single line here, this red shows up here. This little green blue color shows up here. This bluish color shows up here. This purple shows up here. So we see every single line. There's one more right there. So we see every single line reappear. So in this case, those lines reappear. We could put both of these back together and we would have the full white spectrum. So what goes on is hydrogen, when light goes through hydrogen, it absorbs these specific wavelengths. But that energy is excited and it actually emits and gives off those colors when you kind of create a lamp out of hydrogen. And when I say a lamp out of hydrogen, what I'm talking about is taking something like this is filled with hydrogen right here. So there is hydrogen in here. And we essentially just crank some energy through it. So They've got a positive and negative end, and we run electricity through it, and it's kind of like a fluorescent light bulb. So what you see is this is hydrogen, this is the hydrogen lamp, and it gives off this like purplish color. And so when it gives off this purple color, all of this, we don't really care about any of this, is basically just what we saw collimating, creating a line of white light. But what we see is the hydrogen lamp itself creates those 4 different colors: red, green, blue, and violet, in those very specific wavelengths. Okay, so why does it do this? As it turns out, what we see is I have my atom in the center, and I have a bunch of electrons that are around the outside. Let's see here, it's a little hard to draw. And those electrons, when they get hit by energy, they go up to the next energy level. And this gap corresponds to one of these wavelengths. Okay, so that little gap right there, put n equals 1. There we go. That gap right there is going to correspond to the blue light. Okay, there we go. So what does this have to do with anything? Well, what ends up happening is we realize that energy is quantized. But you did not think you would hear that word when you started listening to this. Energy is quantized. All that means is energy is only allowed to have very specific wavelengths, very discrete wavelengths. Okay, so what I equate this to is energy is quantized is if you're an electron and you're on the first floor of a building, you're an electron in this analogy, you go up to the second floor and you get off there. Okay, so an electron can start on the first floor and it can go to the second and it can stay there, right? And then if it wants to go home or go back, it'll go down to the first floor and off it goes. It can go to the second floor, it can go to the third floor, fifth, wherever it wants to go, all the way out to infinity. So it can go to any floor that it wants. What it can't do is it can't stop halfway in between. I can't go up 1.5 floors and get off right there. Electrons are the same way. They can change energy levels, but they're not allowed to be in between energy levels. So energy is quantized is just that simple analogy. You're allowed to be at very specific energy levels, 1, 2, 3, 4, 5, but you can't be in between. And what the chemists did is they realized, okay, we can actually explain every single line using this equation. So the lambda here is wavelength. So wavelength of lights, they're very specific. So that one's 486 nanometers, and we usually use nanometers for wavelengths, but there we go. So 656, so on and so forth. So that is the wavelength. So 1 over the wavelength of light equal to this constant out front, 4 times the value of n, where n is an integer. So n can go anywhere from 1, 2, 3, 4, all the way out to infinity. The idea being that those are the different floors that you're allowed to be on. Okay. It's a little more complicated than this, but this is the idea. So we can explain every single one of these wavelengths with this equation right here. Okay. And it's interesting because these are the floors that you're going to be on. All right. From that, they came up with the development of these equations, or these equations are also part of it. You will always get these equations. I will always provide these to you, so you just kind of have to be able to read them. H is known as Planck's constant. C is the speed of light. Again, lambda is the wavelength. Okay. Again, we have Planck's constant. And we have V, which is going to be frequency. And that's actually new, but frequency. So what I can pull out of this is the following. The energy of light, or really the delta electron. So it's the gap between them. So this is like going from if this were the little circle I was talking about, going from 1 to 3, the energy to go from electron to go from 1 to 3, that's what we're calculating with this. So the energy of that light is equivalent to hc over wavelength. If I'm given a wavelength, I would use that equation. If I'm not, if I'm given a frequency, the energy of the light is equal to h. There we go. Okay, good. In fact, we can look at, we can just simply say, I know that c is the speed of light, which is in meters per second. And typically that's going to be let's see, wavelength times frequency. So we're going to talk about these things, and those are just rearrangements, but these are the important equations to get. We're going to do some examples with these. In fact, we're not really going to have to use these so much, but I'm just showing you that we can associate energy with colors of light. We can associate energy with a frequency of light and all of this other stuff. But ultimately, the idea is energy is quantized, and that's all you need to know. Energy is quantized from all of this. Okay. So knowing that energy is quantized, we start to look at what this actually looks like. So here's this nucleus and these 3 orbitals, 1, 2, 3. In fact, we can actually number them. The first, I'm going to say n is equal to 1, or the n value, we're not going to get into what that is, but that is n is equal to 1. So the circle that is the orbital that is closest to the nucleus is the n equals 1. The next one is the n equals 2. And then finally, n equals 3. And we can keep going 4, 5, 6. And what you notice, some things you might notice, is they're getting closer and closer and closer together. So n equals 1 has one line. So not complicating anything. Again, this is the n equals 1. And we're going to call this the S line. Okay. We'll get to what these lines are, the S, the P, the D, the F, but they're all they're going to be kind of self-explanatory. So every single, with n equals 1, you have just that one line there. Okay. The reason that we have to do this is only 2 electrons can actually exist in the S. So S can only have 2 electrons. Okay. Next up, if we look at n equals 2, we have an equal number of, so this is the n equals 2. We have this, if we zoom in, we actually see 2 bands really close to one another. Energy is still quantized, but that's the idea. This line, the one closer, is called the S. The one that's further away is called the P. And so what we see for n equals 2 is we notice that it can actually hold, there's my 2 s electrons. And the P can hold 6 electrons. So the fact that the P can hold 6 means that when n equals 2, it can hold a total of 8 electrons. When n equals 1, it can hold a total of 2 electrons. Okay. And then finally, the most complicated one is the n equals 3. When I end up with the n equals 3, at least for our purposes, n equals 3, the closest one is the S. The next one is the P. By the way, the first one is the S. The second one is the P. And then the last one is the D. The S can hold 2. The P can hold 6. And the D can hold 10 for a total of 18 electrons. Okay. So the D can hold 10 electrons. So what we see, what you need to take away from this little diagram is, as we proceed out further and further, these lines are the n equals 1, n equals 2, n equals 3. They are suborbitals inside of them. So if this is if these are the orbits, orbit 1, orbit 2, orbit 3, these right here are known as the suborbitals. Okay, and they're going to hold X amount of electrons. You don't need to memorize any of these numbers. I'll show you how to find it on the periodic table super easily. Okay, great. So what we end up with is configurations like this. So we have to talk about energy, come back to the idea of energy. That first line that I showed you, that was the S, okay, as in the orbital above. This first line is just the 1s. And in fact, we can zoom in here because this is n equals 1, we would call this the 1s because it's in the first orbital. The second orbital, we're going to call this the 2s and the 2p. And this would be the 3s, 3p, 3d. Okay, and next the line would we have 4s, 4p, so on and so forth. So what we notice is, and there's a couple of rules we're going to talk about shortly, but here's my 1s, here is my 2s band, or 2 band, right? N equals 2. And here is my n equals 3 band. And these energies, what we'll notice is energy increases as we go up. We are going to put electrons in these things, but we're actually going to represent these electrons with arrows. So there's 2 types of electrons an orbital can have. That is a spin up electron, and this is known as a spin down electron. You don't have to know anything about the spin and what it means. It's just there's an up electron and there's a down electron. Each of these orbitals can hold 2 electrons each, 1 spin up, 1 spin down. So each of these little sections here can hold these little orbitals. So let me back up just a second. This right here is going to be your shell. Shell is equal to n equals 1. This shell is equal to n equals 2, and this shell n equals 3. These little parts here are my subshells. Subshell 1s, subshell 2s, subshell 2p, and then these individual things are known as orbitals. An orbital can always hold 2 electrons, and that's it. Okay? All right, good. So we put 2 electrons in each of these orbitals, 1 spin up, 1 spin down, 1 spin up, 1 spin down. And notice that I am doing a couple of things. I'm filling from the bottom, the lowest energy first, then the next one, then the next one, then the next one. So we're going to keep filling by order of energy. Right? So this one fills, then this one fills. The next one is going to go here at spin up, and it's fine to do a half arrow. It's just easier to write than 2-sided. Spin up. So the next question is, okay, where does my next electron go? Does it go here because it's the same energy, or does it go here? Do I fill up all orbitals before moving on? Okay, so that is the question, and we're going to answer it in just a second. So we know the first 2 go in the 1s because it's the lowest. Then the next 2 go in the 2s because that's lower than that. And now when we get to the 2p, I put 1 electron in the first orbital. And now the question is, does it go in the second, or do I put the spin down in that one? Okay, so there are 3 principles we use to fill up our orbitals. Okay, so the first one is the Aufbau principle. The Aufbau principle is the filling up principle. So the German word Aufbau comes from it's roughly translated as to construct or to build up. Okay, so in this case, the Aufbau principle basically states that we are always filling the lowest energy orbital first. By the way, this is always for a neutral atom, and it will always be the same for you. It's not really going to matter, but that's for neutral atom. Okay, so, and that's what we've been doing, right? We started with the lowest and we start to fill. Next up, the Pauli exclusion principle. Okay, the Pauli exclusion principle is just a simple idea that if I have an orbital, a little smaller. If I have an orbital, okay, there is only one way that can actually fill. So I can have 1 spin up, 1 spin down. I cannot have 2 with spin up. I cannot have 2 spin down either. Okay, so that's okay. This is not. This is not. So when you have an orbital with electrons, it can either be spin up, spin down, and that's it. You can't have 2 spin down or 2 spin up in the same orbital, in the same level or shell or subshell. Yes, but you can't have them in the same orbital. It's the same spin. This has to do, the Pauli exclusion principle has to do with quantum numbers. Okay, so the Pauli exclusion principle basically says you have to have a spin up and a spin down to fill an orbital. That's it. And then finally, Huns rule. Huns rule is where we're going to talk about now, is when I have an orbital like this, I have two choices. We said our first is always going to go in any one of the orbitals. The second, does it go here or does it go here? Okay. Well, that is correct. That's wrong. The Huns rule, basically, Huns rule of maximum multiplicity, is what we want is most unpaired electrons possible. So if I have a choice, I want to have them unpaired. This electron right here is considered unpaired. This electron right here has a partner. It has a pair. So if I have a choice, I always want to basically what it says simply is fill up an entire shell before you proceed. So here I have my first electron. We found out the second one goes here. The third one goes there. The Huns rule basically says fill up as many orbitals as you can before you go and start to pair. Okay, so where does the next electron go? Right there, boom, and this is how we fill up. Okay, so that's the idea behind. We always start, again, the Aufbau, we always start at the lowest and we work our way up. Pauli exclusion principle, we only do spin up, spin down. And then finally, we always try to maximize the number of electrons. I'm not going to put it here. I'm going to fill those edges first. Okay, good. So with that said, we are going to look at this in class. So please, hopefully you've watched up to 5.2. 5.2 we're going to do in class. And then I'm going to have another video after we get through class to talk about the periodic trends. All right, great.